Great, thank you very much. I'm US technical lead at NuQuantum, and I'm going to introduce you all to what we're doing at NuQuantum for photonic systems for distributed quantum computation, creating individual entanglement links between processes to create what we call the entanglement fabric. So as I was saying before, we span out to the University of Cambridge in 2018, and we're now a multidisciplinary team of 60 people, mainly based in Cambridge in the UK. Our technical team spans 9 disciplines from theory to photonics through mechanical engineering, which allows us to build technology for the full quantum networking stack. And we've also recently expanded into the US, opening an office in Los Angeles. We're building photonic technology because we see that there is a huge potential in quantum computing to help us model more complex and more highly correlated systems than can be modeled by classical computers. And this will open up new applications from drug discovery, material science, decarbonization, all the way through to enabling better AI models. The most transformative applications rely on a very large number of error-corrected qubits, requiring potentially hundreds of thousands to millions of physical qubits. And this is very hard to do in one single quantum processing unit with the technology that we have today. Our model for building a large-scale system that can begin to address these problems is to break the large million-qubit computer down into smaller pieces. We call this distributed quantum computing, and that means taking a monolithic processor and connecting it to many others using photonic interconnects. This is a pattern we see in classical computing as well, where the largest supercomputers are built in a modular, distributed way. And our entanglement links are fundamentally built on photons because photons are natural carriers of quantum information. They're easy to move around, hard to interfere with, and relatively easy to process and ultimately to detect as well. Our architecture for photonic networking of quantum processing units is in 2 parts. So first, we need to extract photons from the matter qubits inside the processors. And then we need to route the photons through a switching fabric and finally into an array of Bell state measurement devices that can perform a joint measurement on the 2 photons, projecting the matter qubits into an entangled state. On the photon extraction side of the equation, so down at the bottom here, we need to ensure that this part of the process happens with the highest possible efficiency. To do this, we have built a qubit to photon interface based around our optical microcavity technology. Our cavities have a finesse of up to 200,000, and we can stabilize their length to within 80 picometers, which is needed to ensure the photons coming from different QPUs are indistinguishable. Our investment in the technology at the qubit to photon interface level helps to ensure that we can reach success rates that don't necessitate quantum memory elsewhere in the system. And we built this system for both neutral atoms and for trapped ion qubits. Once photons have been extracted, the next step is to route them through a switching fabric and perform a Bell state measurement to produce the entangled link. We call this a dynamic entangler, as it allows dynamic reconfiguration of the entanglement graph that is produced between different QPUs. We have also developed a scalable control system that can react to heralding events in real time and distributes highly accurate timing using CERN's White Rabbit protocol. And we've implemented this in hardware suitable for testbed deployment as the center of our 4-node quantum network. Currently, fiber optic components can be used for this small scale system, but to get to a fault-tolerant machine, we'll need technologies that can scale better than that. That's why we're also developing a thin-film lithium niobate photonic integrated circuit that will replace the optical module in our quantum networking unit, allowing us to scale to larger channel counts and larger numbers of QNUs in a utility scale machine. So what challenges do we face in developing the photonics for this application? Well, the first is preserving the high fidelity provided to us by trapped ion or neutral atom QPUs. While our work on distributed error correction tells us that the non-local link fidelity can be a lot lower than the fidelity of local gates, which would be in sort of 4 to 6 nines region, we still need to achieve a 99.5% fidelity across our entanglement links. Our first gen QNU already exceeds this threshold, and our photon extraction and entanglement scheme will maintain this across real QPUs. The second challenge is maintaining a high rate to ensure that decoherence does not limit the performance of the computing system. Again, we can look to quantum error correction theory to tell us how fast we need to be, and the answer is that a success rate around 25 kilohertz should exceed requirements. We also want to overshoot that by as much as we can, so we're targeting a 1 megahertz attempt rate. Then, to ensure that as many attempts as possible are successful, we need to address all the sources of loss and latency in the system in the modulator's detection system and minimize latency in the control system as well. And of course, packaging is an important factor, as fiber chip coupling is an important source of loss, We have additional requirements, things like cryogenic compatibility. I've included an image of the sort of system in our lab that we need to package our PICs to integrate with. And finally, I'd like to talk about some of the technologies that we are using to build our photonic integrated circuits. Our switching fabric requires high speed and compatibility with 1 micron photons naturally emitted by the ion traps. Therefore, thin film lithium niobate is a really enabling technology that allows us flexibility around operating wavelength while maintaining high speed and extremely low on-chip losses. We are also developing on-chip superconducting nanowire detectors that offer us a scalable on-chip option towards the highest efficiency single photon detection. And all of this is, of course, available to us in a platform that is inherently manufacturable and scalable, allowing us to leverage technology developed for the semiconductor industry and to make best use of foundry services that are becoming available for these new photonic materials. So I hope that was an interesting introduction to photonics at NuQuantum. Apologies for the unstable internet connection. Please feel free to reach out to us to talk about collaborations and if you've got any more questions about what we're doing.